Hello, everyone. Let's start today's session. I hope you all had a great day so far. Today, we are gonna talk about resistance, how we can read the resistance, how we can measure uh, the resistance of a resistor, and how what's going on if we have some resistance in series or in parallel. We are going to talk about that and look at it from the experimental kind of like perspective when you want to like actually measure instead of calculating using the formulas. And also we are going to talk about some like complex maybe circuits diagram. So we make sure that we understand how to measure the resistance of the resistor, how to simplify the network of the resistors, and learn how to measure the equivalent resistor of a network, since it would be very useful when we wanted to like discuss the Thevenin and Norton theories for next in the next week. Now, work with me. Let's start with the basic. What is the electrical circuit? Okay. The official definition of an electrical circuit is a closed loop that allows for continuous flow of electrical current. Okay. So we would have some basic circuit component that could include like power sources or conductors, resistors, loads, capacitors, inductors. There are several passive components and also several active components, which you are going to learn after the midterm about them. And most of them, all of the actually these components basically have their own reaction, their own IV characteristics, their own formula that relates the voltage across them to the current that passed through them based on a certain condition or input. Are we good? So far, this is the definition, very simple. Now, we have three key electrical parameters when we talk about the DC system. One would be voltage. You already are familiar with that. But to be precise, voltage is the difference between the potential of 2 points, the difference between the potential of 2 points in our circuit. I'm emphasizing the 2 points because sometimes we tend to say like, okay, point A caused by this amount of voltage. That's not precisely an accurate statement to make, okay? When you do that, basically what we mean is that the potential difference of that point A and the reference, or we call it ground, is going to be that level of the volt. So voltage always is between the 2 points, meaning it has value and direction. Are we good? So it's not a scalar, it's a vector. Okay, now, next parameter that we care a lot when we talk about the DC analysis of circuit is current. Again, these are kind of like very simple. You already are familiar with the definition. We are going to review them. Now, current is the average of the charges that flow through the circuit. So you have some like N charges that moving randomly through your circuit. It's random, okay? When your direction, I want to open a part. When the direction of the current is that way, that doesn't mean all the charges going down. It's random. But the average of those movements has a one direction, which we call it current. Okay, and the value of that average is current. Okay, so remember that. And there is another part that says when we talk about the movement of the charges, the general assumption we consider the electrons as the charges that move energy. Okay, but I want you to know, and this is kind of the misunderstanding. The direction of the current that we show in the circuit is not the direction of the movement of electrons, is the direction of the movement of the positive charges. Okay, so if the direction is direction of the current is from left to right, that means electrons going from right to left. Okay, it is because of the definition. Centuries ago, they defined the current as the movement of the charge. That was before they knew actually the electron exists. Okay, so they consider the positive charge as charge and negative charge as absence of positive charge. Okay, so this is kind of like the reason. Now, one other component in DC analysis is resistance. Now, you already know that resistor is not the only passive component that we have in our circuit. You might heard of inductor or capacitor. Okay, now why, when I wanted to list the key electrical parameter for DC measure and DC circuit, I didn't mention the capacitor and inductor. I only mentioned the resistor. Anyone can go ahead.
Because they're only applicable on DC.
There are only applicable in AC. Yes, that's correct. Now let's restate that fact. That's true. When you have a DC component or DC circuit, capacitors behave as an open circuit, and the inductor behave as a short circuit. So basically, they are not working in your circuit as a component. They are either open circuit or short circuit. So when we talk about the DC circuit, basically they don't affect the dynamic of the system, the steady state of the system. Now, another parenthesis. When we talk about the DC analysis and the DC circuit, we have a steady state, which is DC, which what we know as DC, but within that same concept, we have some transient. When you shift from a certain level of the DC to another level of the DC, like voltage changes from 0 to 1 or 1 to 2, that incidence of change is transient. In that change, no capacitor and inductor works. You can ignore them. We are going to talk about that in, I think, third week or fourth week. Maybe fourth. I'm not sure. Okay, look. This is going to be another discussion that we are going to have. I just wanted to like open the parenthesis that when we say DC, we mean the DC circuit that is in a steady state. All the transient and changes are done. Our system is in a steady state. Is that clear? Are we good? Now, another factor that we normally consider when we want to like analyze or test an electrical circuit, especially in the lab, this is very important. The two parameters are power and energy. They are related to each other. Energy is the power consumed by the component during the time. So P times T, okay, P multiplied by time is going to be the energy. So if the watt is the power consumed during a certain interval of time, we call it energy. Now, why the power is important? Power is basically the rate which energy is consumed or transferred. Why is important? We are dealing with some physical components. They are not ideal. It's not like you can apply any value of the voltage across the component or conduct any value of current through them. They have a physical tolerance before they burn. So they have a capacity of absorbing power or transferring power. Very good. So that's why the power is also one of the important parameters. So when you want to design or test or choose a component to put in your circuit, you need to pay attention that you do not exceed from the nominal power of that component. For example, like in this Rick lab, you are going to place some resistor and you are going to supply some energy from your DC voltage source, meaning you're applying a voltage and you're conducting some amount of current through that resistor. Okay? That voltage time current means you actually injecting a certain amount of power, okay, into that resistor. Now we have like a quarter of a watt resistor in the lab, we have half a watt, 0.5 watt resistor in lab, or we have also like a load resistor which can tolerate more than that. Okay, when you want to like tune your DC source, you need to pay attention. Okay, I have a quarter watt, okay, 0.25 watt resistor. So whatever voltage that I apply to, which would result in a certain amount of current, the multiplication of them should not exceed that capacity of the resistor. Does that make sense? So this is why we pay attention to the power all the time. Otherwise, you're going to burn your circuit. We said we have several types of components. I'm not going to go deep into that, just listing that. We have active and passive components. Okay, the passive components are resistor, different type of resistor, capacitors, inductors, switches. The component that they not actively change the IV characteristic, current voltage characteristics. So they just passively follow the circuit rules. Okay. In active circuit, we are in active components, we have different kind of like behavior. Okay, we are going to see that later on in this, during the course. Now, this specific week, we are going to focus on resist. Okay, resistor basically is the component that withstands the current. Okay, it's in the neck. Okay, if you apply a certain electrical field or voltage across your system, across that resistor would try to resist against conduction of the current. Okay, now that being said, one of the most important application of a resistor in your circuit is when you want to like actually limit the current to a certain value. You might have some like sensitive device in your circuit that you want to make sure you never exceed a certain threshold of the current. So you use that resistor, a series resistor with that component as a safety factor. So you make sure that worst case scenario, we are not going to exceed a certain threshold for current. This is the most popular and most important application of a resistor. Now, resistor would have several types. It could be constant, it could be variable, which the variable one we call it potentiometer. Okay, you can change the value of the resistance. Okay, you are going to work with that in the lab also. There could be different material in it. It could be like a carbon-based resistor or metal film resistor or wire bond resistor. Each of them has their own characteristics, okay, and give you a certain level of accuracy when it comes to the resistance of that resistor. Okay, now when you work with a resistor, especially the one that has a fixed resistor, okay, on that resistor, you normally see a bunch of color band. Okay, those color band are the codes that help you to basically understand what is the value, what is the nominal value of that resistor. Okay, so there is a table, as you can see, to read the color and know what is the value of the each color is. Okay, what number is coded by each specific color. When you look at the resistor, the way that you can read the colors is that there are several bands. One of them is tolerance. Okay, you have to hold the resistor in a way that the tolerance is at the right end. Okay, now how you can find, how you can kind of like recognize which one of the two end color are the tolerance and which one is the one of the digits. All the other bands have equal distance from each other. Okay, the tolerance band has more distance from the next color. You can see here that this distance, the distance of the tolerance band from its neighbor is relatively more than the other distances. So that way you can recognize which one is the tolerance band. Are we good? Now, when you look at the resistor and you have your tolerance band at the right side, there will be either 2 or 3 lines that actually represent digits. Okay? So the 1-digit line, the first one, the second one, and the third one. And there are going to be another band following those 2 or 3 digits, which we call it multiplier. Now, how we can read it? Those digit bands are numbers. So it's exactly whatever code you have. Like if you have a black, it's 0. If you have a brown code, it's 1. Red is 2. So it's specifically that number. So this is an example in the top of the image. Okay, so we have, like, for example, the first digit line is yellow. Yellow means 4. So what we have to do is that, okay, this band worth 4. The value is 4. Next one is the second digit band. Is purple. It's going to be 7. So we just write 7. Okay. Now, if you don't have 4-digit band beside the tolerance band, if you don't have 4, always 1 next to the tolerance is multiplier. So that way you can find if this one is digit band or multiplier. So the band next to the tolerance is always multiplier. Now, what is multiplier? Multiplier, whatever color code you have, it means 10 to the power of that color code. So, black is 0. So if you have black, it means 10 to the power of 0, which means 1. Correct? Or if it's brown, it's 10 to the power of 1, which means 10. Are we good? So you just multiply that by that number. So now we have 47 kilo O. Okay, this is how we read that. 7 times 1000, 47 kilo O. and we have, this is gold, so the gold color, so we have 5% of tolerance, meaning the actual value should be within the interval of plus minus 5% of that nominal value. Are we good? Let's try the bottom example, this one. The first band is orange, which means 3. The second one is green, which means 5. Now, we have the third one here, you can see that, which is black, which means 0. And the multiplier is red, which means 10 to the power of 2 or 100. Now, if you read that, it's going to be 35 with 30, which is kilo. Are we good? And the tolerance band is brown, so it's 1%. So it's plus minus 1%. Are we good? So this is the way you can read your resistance. There are going to be I think the first task that you have in the lab assignment is actually reading such numbers and then measure it in the lab to see to see what is the meaning of that tolerance and how close one resistor could be to the nominal value. Okay. Now, any questions so far about the resistor or how to work with that color band? No, are we good? Okay. When you want to work with a circuit lab or any type of theoretical analysis of a circuit, there are 3 main theoretical laws that you need to be fluent in order to run any type of analysis over a circuit, over an electrical circuit. The first one, which is the fundamental one, is the Ohm law, which relates the voltage and current to each other. And we know that the voltage and current for a resistor is going to be voltage equal R times current. Famous formula that you probably work thousands of times during your courses. Okay, so look into the physical. I encourage you to look into the physical equation of the Ohm law. It has a lot of beautiful concept in it. Okay, so it's not just a simple V equals to IR. There is a physical background to it. The actual Ohm formula is in one of the Maxwell equation, which is very kind of sophisticated equation. So this is basically the very simplified version, that voltage equal to Ri is very simplified version of the Ohm law. I really encourage you to go through that. Now, the other 2 theory that you need to work with is the KVL, the famous KVL and KCL, the Kirchhoff laws. Okay, the Kirchhoff laws are based on energy conservation. Okay, the KVL says when you travel through the loop from a starting point all the way and go back to the starting point again, that means your potential should not be changed at all because you started from a certain point and you ended at the same specific point. So your potential should not be changed. What that means? That means whatever difference of a potential you experience through that loop, all of them together should add up to 0. Sometimes you gain potential energy, sometimes you lost potential energy. All those gain and loss add together should be equal to 0. Okay? Now, when you want to run the KVL over a certain loop, the KVL says that the summation of those VIs is equal to 0. How we can do that? The simple way, I don't know if you know the trick or not, the simple way is that you start from here, you start running over the circuit and come back. So this is a loop. When you get to the certain component, the polarity that you exit the component is going to be the polarity of value. So if this is Vs, when you wanted to write this sigma, it's going to be plus Vs. Now you get to the first resistance, current going that way because we are going that way. So that means this is the higher, what happened? This is the higher potential, this is the lower potential. You're exiting from the negative polarity, so it's going to be minus voltage across R1. Same goes for that one, minus voltage across R2, and this is equal to 0. This is like a simple trick to like, don't mess up the polarities, okay? So running the KVL is one of the most fundamental tools that you have for analyzing the circuit. Again, another aspect of energy conservation is the KCL. And is very simple. Whatever charge you pour into a node should be equal to the charges that you drain from the same node. Okay? You have a specific node. If you pour in current 1 and you drain current 2 and current 3, at this specific node, we didn't create any extra charges and we didn't consume any of those charges. So what we poured in should be equal to what we drain out. That means I1 should be equal to the I2 plus I3. Now, the official formula is same as KVL. Sigma of the currents should be equal to 0 regarding the direction. So if it gets in, positive, if it gets out, negative. Okay? Now, I want to ask a question. Actually, no, let's because I'm not sure that you are heard about that. No loss is general when you talk about the physics. When probably you taught about the KVL and KCL, you were taught that, okay, you can always use the KVL and KCL in your circuit. Not true. Okay? KVL and KCL happen if the frequency of your electrical wave is relatively small. The wavelength of that electrical wave, which is 1 over frequency, is relatively small regarding the dimension of the actual dimension of the circuit. The rule of thumb is 10 times. So if your wavelength of the circuit is 10 times, it's 10 times the dimension of your wires and the whole circuit, then you don't have KVL KCL. Anyone knows why is that? Any idea? Because after that threshold, you don't conduct the energy. You don't only conduct the energy, you also have a radiation of it. So your circuit becomes antenna. Okay? So now there might be, like, at a certain frequency, there might be some radiation of energy here and there. Now the KCL doesn't exist, doesn't hold true at that point. You see? So this is additional kind of like information to know. Any questions so far? No? Now let's talk about how we can actually develop network of resistors in our circuit. Very simple. We have either resistors that are connected in series with each other, or in parallel with each other, or the combination of it. Okay? When you have resistors in series, I believe you already know that you can simplify all those series resistor with an it's R1, R2, R3. You can simplify that by an equivalent resistor, which is the summation of those resistors. That was the series, right? Now, how you can theoretically prove this is the right formula? You run a KVL here, and you find out what is the resistance that you see from these two terminals, which is the voltage across these two terminals divided by the current that you inject in this terminal. Now, run a KVL, you will reach this formula. Okay? Now, when you have such a connection between the resistor, the total voltage across the terminal would also divide between the resistor based on their value. How would be the voltage divide? What would be like, for example, let's say we have here we have voltage S at between these two terminals. What is the voltage across the second resistor?
The second.
Perfect. Okay, so the voltage division would be the ratio, like V2 would be that Vs times R2 over the summation of the Rs. Why? Because this is the current passing through the circuit times the resistor is the voltage across it. Now, if we have in parallel, what happens then? If you have the parallel of some resistor, what's happening is that you can calculate the R equivalent, okay, based on the inverse of those resistors. Okay, it's come from the KCL. You run a KCL and this node, you will end up to this equation. So it's going to be 1 over R1 plus 1 over R2 plus all others, all of the resistors, inverse of all of the resistors. Are we good? Now here you have a current division. Okay, what current will divide the behavior of the current division and voltage division are the opposite. So in the voltage division, if your resistor was higher, it would have the biggest portion of the higher portion of the whole voltage. But in current division, as much as your resistor is higher, it would get lower portion of the whole current. Make sense? So it has a. You can also use the formula of the KCL and the voltage and Ohm law to find the values of current division. Now, if you have a complex system, you just need to step by step apply each of these two to a subsystem to simplify the subsystems, and then move forward step by step to simplify the whole system to a one resistor. We are going to see that in one of the examples in our lab assignment. Now, let's go to the lab. Let's talk to the lab. What are going to happen in our lab when we want to like read a measurement, read a resistor using measurement. Okay, you have your ohm meter or digital multimeter. When you want to like read the resistance, first of all, the connection of the probe should be parallel. So your digital meter should be parallel to your resistor in order to read ohm. Okay, so we are going to connect, for example, we have this resistor here, and we want to measure it. We are going to connect the probes that relates that is used for measuring the resistance, which is the O socket and the common socket. So you connect one to one end and another one to another end. Now your multimeter is in parallel with your resistor. Since it's DC, it doesn't matter which way you connect, it's going to be the same resistance. Okay, so the polarity doesn't matter for the resistor. Okay, now it's a multimeter, so you have several options. You need to choose the proper option, which we have here. Okay, but that's not it. We already talked about that. That multimeter have several ranges. Using the range option, you need to set the range of the measurement to the margin that you expect to have the value. Like, for example, this is 35K. Okay, so you might want to choose a range of kilo ohm in your multimeter. Are we good? If you wanted to measure a 100 ohm or 10 ohm, you would change the range to the O range. Is that clear? Are we good? Okay. So be careful about the connection and be careful about the range. Now, one of the very simple mistakes that you might make is holding the probes and the resistor with your hand. The resistance of your body is very high relatively to very low to the resistance that you have. So when it comes to the parallel resistance, it wouldn't change the values much, but it would enter some error if you're making. So do not hold the resistor in hand. Very good. Now, another fact, when you want to measure a resistor, there should be no active power source in your circuit. That also would affect your measurement. So everything is off, we are de-energized, and then we are gonna measure that resistance. And if you want to measure a specific resistor within the home circuit, you need to disconnect that, because otherwise you are gonna see the equivalent resistor from that pair. Does that make sense? So remember those stuff. You are gonna have these three circuits in your lab assignment. Very simple. You have a pre-lab and in-lab. The pre-lab is theoretical calculation. So you have the values. You are going to calculate the equivalent resistor that you might see from the terminals. Okay? This is series, this is parallel, this is complex. Are we good? And then in the lab, you are going to make these circuits before you put the resistor on your breadboard. Measure the actual resistance of each of them, because they are not going to be equal to the nominal value. They have a tolerance. We have a tolerance. Okay? So measure those so you know actually what's going to happen in your circuit in reality. Then build up your circuit and measure the values that you want. Are we good? Same goes to the parallel one. Any question? No? For the third one, which we have the switch in the system that changes the circuit, you need to first do the analysis and the measurement for the switch to be in the position of S1. When you're done with that, then you change it to the S2 and you do all the analytic analysis, theoretical analysis, and the measurement again. Because you have two different circuits. Are we good? And all the steps, individually measuring those resistors and then measuring the equivalent is common between all the exercises. So you need to pay attention to that because you need to actually first calculate theoretically based on the nominal value, what is the equivalent resistor. Then in the lab, you're measuring that. And in after lab, you are recalculating your theoretical value based on the actual resistance value. So that, like, for example, that 470 might be 466. In pre-lab, you use 470 to calculate. After lab, you have to run the calculation again with 466 that you measured in the lab. Make sense? So this is what's going to happen. I also put some tips for minimizing the measurement. Go through them, and it would help you to avoid some mistakes. I already uploaded the PPT file on Canvas, so you have access to that. Any questions? No? No. Yeah. I believe you have 2 or 3 of each of resistors in your package that you're going to get the first time you are in the lab. If you use the same resistor, it's not going to change. There are going to be some measurement error, by the way, which brings the uncertainty principle into hand. All your measurement through the semester, you have to calculate the uncertainty of your measurement. We are going to be a professional engineer. Okay, it's not just haphazard measurement, working like just reporting some numbers. Okay, you have to always calculate the uncertainty of your measurement, each of the measurement, meaning you have a statistical analysis over your own measurement. Now, I have a video, and I think I believe I posted that on Canvas on the preparation module that tells you how to actually calculate the uncertainty of a certain measurement. Okay. During that video, we have uncertainty type A and uncertainty type B. I don't expect for you to uncertainty type A would be anything but 0. Okay, because nothing would change. It's very rare that you would have an uncertainty type A in your circuit. Okay, but uncertainty type B is not going to be 0. I'm telling you this technology. If you didn't watch that video, go watch them. You need to calculate those uncertainty for your lab assignment. Okay. Any other question?
They're like standard that we should use.
We kind of consider that already. This is a general clip. Now, how you can do that is you have 17 stations in there. Okay, you can work with each other, borrow your friend multimeter, and see if they match. You know what I'm saying? So we already calibrated those devices. Okay, but if you like, this is a professional kind of like. If you want to do that by yourself, borrow one, or use oscilloscope. When you know the current, you're measuring the current from multimeter. You're seeing the voltage on the oscilloscope, and you can calculate the resistor. Okay, so you have multiple measurement device that you can use and compare which one is more accurate, which oscilloscope is more accurate than the multimeter. So you can use that as a reference to calibrate your a multimeter error. Any other question? No? Okay. So